Welcome to a journey through the wonders of the universe, where the mysteries of space and time await to be unveiled. Over the next 4 hours, you'll be guided through fascinating stories about comets, the secrets of Saturn, the phenomenon of space weather, and the powerful solar storms. Relax your mind, listen closely, and let the knowledge of the cosmos gently carry you into a deep, peaceful sleep. The vast universe holds not only mysteries, but also a profound sense of calm. Let's begin our exploration together. Chapter 1: Comets' Secrets. We share our solar system with the remnants of a time long past, debris that dates back to the very birth of the Sun and its planets. These celestial wanderers, comets, are like silent travelers, hurtling through space at speeds exceeding 20,000 miles per hour, invisible to us until they are warmed by the heat of our Sun. Darker than coal, these icy bodies seem inconspicuous and harmless at first, but their history and potential tell a story both awe-inspiring and terrifying. Comets hold within them some of the oldest, most pristine material in the solar system. Born 4.6 billion years ago, these icy time capsules have remained largely unchanged, carrying evidence of what the early solar system looked like before planets formed and life began. Locked in their frozen cores are water, carbon dioxide, methane, and other organic compounds, the very building blocks of life itself. Some scientists believe that comets may have played a pivotal role in delivering these essential ingredients to Earth through repeated collisions. Without comets, the Earth as we know it may not exist. Their impacts, while destructive, could have helped shape the planet's atmosphere and oceans, providing water that is crucial to sustaining life. They are not just the harbingers of doom that ancient civilizations feared, but also potential architects of our very existence. As such, comets are often seen as both the creators and the destroyers, a duality that continues to fascinate astronomers and planetary scientists alike. To understand the magnitude of a comet's power, we only need to look into Earth's deep history. Roughly 65 million years ago, a cataclysmic event changed the course of life forever. At that time, dinosaurs ruled the Earth, having dominated the planet for over 140 million years. Then, without warning, their reign came to an abrupt and violent end. Scientists widely agree that a 6-mile-wide comet or asteroid struck the Earth near what is now Mexico's Yucatan Peninsula, traveling at a staggering 20,000 miles per hour. The impact unleashed the force of 1 trillion tons of TNT, equivalent to millions of nuclear bombs detonating simultaneously. The immediate devastation was unimaginable. Entire regions were obliterated in seconds. Enormous tidal waves surged across continents, and shock waves triggered global earthquakes and volcanic eruptions. Yet the initial destruction was only the beginning. Massive amounts of dust and debris were launched into the atmosphere, blocking sunlight for months, perhaps even years. The global temperature plummeted, turning Earth into a frozen, barren wasteland. Plants withered without sunlight, starving the herbivores that depended on them, which in turn spelled doom for the carnivores at the top of the food chain. The oceans were no sanctuary either. Marine ecosystems collapsed as plankton, the foundation of aquatic life, vanished. This cataclysm wiped out nearly 75% of all species on Earth. The mighty dinosaurs, who had once seemed invincible, disappeared almost overnight. But from the ashes of extinction came an opportunity for new life. Small, adaptable mammals, once relegated to the shadows, began to flourish. Their evolutionary explosion paved the way for countless new species to emerge. one of which would eventually be us, Homo sapiens. The story of the dinosaurs serves as a stark reminder. Comets, while magnificent, are also capable of wreaking unimaginable havoc. Scientists today believe that Earth is not immune to future collisions. While the chances of a catastrophic impact in our lifetime are slim, the odds over millions of years are inevitable. Astronomers around the world monitor near-Earth objects closely, but as history has shown, these cosmic wanderers are difficult to detect until they are too close for comfort. The question is not if, but when Earth will be struck again. Future generations may face the same peril that wiped out the dinosaurs. Unlike them, however, humanity has the tools to prepare and possibly prevent such an outcome. Space agencies are already studying methods to deflect or destroy potential threats, turning science fiction into plausible reality. For now, as we look up at the night sky, the fleeting glow of a comet reminds us of its profound connection to both our past and our future. These ancient travelers are cosmic messengers, bringing stories of creation and destruction across billions of years. They are the ultimate paradox, capable of extinguishing life, yet holding the secrets to its very origins. As we explore and understand comets, we come one step closer to uncovering the mysteries of the universe and ensuring that life on Earth continues to thrive for millions of years to come. The comets giveth, and the comets taketh away. The dinosaurs didn't stand a chance against the cosmic catastrophe that wiped them out. Fortunately, humanity has a distinct advantage. They had no telescopes, no technology, and no understanding of their foe. But we are different. Our curiosity and intelligence have propelled us to study these celestial wanderers, unraveling secrets that have remained hidden since the dawn of our solar system. Today, we have the capability to send satellites deep into space, intercept comets, and even land on them. These technological marvels represent a culmination of centuries of astronomical inquiry, starting with something as humble as a wooden telescope. Back in the 17th century, British astronomer Edmund Halley changed the way we view comets forever. Observing the motion of a comet in 1682, Halley made a groundbreaking discovery. This comet followed a highly elliptical orbit, bringing it close to the Sun once every 76 years. His calculations predicted its return in 1758, which it did, earning the comet his name, Halley's Comet. Halley's work revolutionized comet science, but even he could not explain where these enigmatic bodies originated. To uncover their origins, we must travel back 4.6 billion years, to the very formation of the solar system. In the beginning, the Sun, planets, and comets were born from a giant molecular cloud of dust and ice spinning in space. Gravity caused the cloud to collapse inward, forming the Sun at its core. The leftover material began clumping together, creating countless comets and asteroids, along with over 100 protoplanets, the precursors to the planets we know today. The next 100 million years were a chaotic battleground. Protoplanets collided and merged, their massive impacts shaping the planets and moons. This violent phase ended with only 8 planets surviving, including the embryonic Earth. But not all material was swept up. Many comets and asteroids were flung to the outermost edges of the solar system by the gravitational forces of the newly formed planets. This distant region, billions of miles from Earth, is what scientists call the Oort cloud. Though it is invisible to us, its presence is inferred by studying the orbits of comets that occasionally venture into the inner solar system. The Oort cloud is believed to be a vast, spherical shell of icy bodies, housing approximately 1 trillion comets. To imagine its scale, if you were standing on one of these comets, The next closest one would be 10 to 100 million miles away. These comets drift in solitude, taking up to 30 million years to complete a single orbit around the Sun. Known as long-period comets, they remain dark and inert, black as coal, hidden from our view. However, their peaceful existence can be disrupted by the gravitational pull of a passing star or another celestial object. Such disturbances can send them hurtling toward the inner solar system, where the Sun's heat begins to transform them into the brilliant, tail-bearing comets we observe from Earth. For centuries, humanity's understanding of comets was limited to what could be observed from the ground. That changed dramatically in 1985, when the European Space Agency, ESA, launched the Giotto satellite. This mission aimed to fly 90 million miles into space and capture the first close-up images of a comet's nucleus. Giotto targeted Halley's Comet, providing scientists with unprecedented insights into its composition and structure. The mission was groundbreaking and risky. As ESA scientist Gerhard Schrempf explained, Giotto's success was far from guaranteed. It was the first planetary mission ever televised, and no one knew what to expect. But the satellite's close encounter with Halley's Comet delivered remarkable results, revealing the nucleus as a dark, icy body, surrounded by jets of gas and dust erupting into space. This discovery transformed our understanding of comets, proving them to be active, dynamic objects rather than the passive, icy wanderers they had long been thought to be. Giotto was just the beginning. Modern missions like NASA's Rosetta and Deep Impact have expanded our knowledge further, landing on comets and analyzing their surfaces in detail. These missions confirm what early astronomers like Halley could only theorize. Comets are key to understanding the formation of the solar system and the origins of life on Earth. As our exploration continues, these ancient travelers remind us of the incredible history they carry, an unbroken link to the very birth of the cosmos. From the simple wooden telescopes of the past to the advanced space missions of today, humanity's quest to understand comets has revealed as much about ourselves as it has about the universe. In March 1986, the Giotto spacecraft embarked on a daring and historic mission, flying just 400 miles from the nucleus of Halley's Comet at a breathtaking speed of 150,000 miles per hour. The journey was fraught with danger. The environment surrounding the nucleus was volatile, and the intense gas and dust ejected from the comet threatened to destroy the spacecraft. Yet, Giotto succeeded, and the first close-up images of the comet's nucleus began streaming back to mission control. The nucleus, an elongated body approximately 10 miles long and 4 miles wide, revealed remarkable structures on its surface. However, the most surprising discovery was how little of the surface was active. Less than 10% of the nucleus emitted gas and dust, while the rest was as dark as coal, a silent witness to billions of years of cosmic history. What causes these icy bodies to transform from dark, inert lumps into dazzling spectacles of light and motion? The answer lies with the Sun. As a comet approaches the Sun, its heat causes the comet's icy surface to crack. The frozen material deep within the comet undergoes sublimation, a process where solid ice turns directly into gas. This gas forms a glowing cloud called the coma, which envelops the nucleus. As the comet moves closer, powerful solar winds, streams of charged particles emitted by the Sun, sweep the gas and dust away, creating the comet's iconic tail, which can stretch millions of miles across space. Despite their immense length, these tails contain so few particles that the entire mass could fit into a single suitcase with room to spare. Intriguingly, no matter which direction the comet travels, its tail always points away from the sun due to the force of the solar wind. This makes comets paradoxical. Though they are some of the smallest objects in the solar system, their tails can extend farther than the 93 million-mile distance between Earth and the Sun, making them both minuscule and vast. Throughout history, the sudden appearance of comets in the night sky has filled humanity with awe and fear. Their unpredictability, coupled with their ghostly glow and dramatic tails, made them seem otherworldly. Ancient civilizations often interpreted them as omens of doom, associating them with disasters, wars, and death. Astronomer Don Yeomans attributes this fear to the erratic nature of comets. Unlike planets that move predictably, comets would appear unexpectedly, light up the skies for weeks or months, and then vanish without a trace. This unpredictability influenced events as monumental as the Norman conquest of England. In 1066, William the Conqueror saw the arrival of Halley's Comet as a divine signal to invade the British Isles. Even in modern times, comets have inspired bizarre and tragic responses. One infamous example occurred in 1997 with the appearance of the bright Hale-Bopp comet. Members of the Heaven's Gate cult believed the comet was accompanied by an alien spaceship meant to take their souls to another realm. Tragically, 39 members of the cult committed mass suicide, believing they would ascend to the spacecraft. While myths and fears about comets persist, scientific understanding has replaced superstition with wonder. Today, we know comets are not harbingers of doom, but rather time capsules, preserving clues about the early solar system and the origins of life on Earth. Comets formed during the earliest days of the solar system, about 4.6 billion years ago, and carry within them the raw materials that eventually shaped planets like Earth. To study their composition, scientists use a tool called a spectroscope, which breaks down light into its constituent colors. Each color corresponds to a specific element, allowing scientists to identify the materials in a comet. What they've discovered is that comets are essentially dirty snowballs composed of carbon, hydrogen, ice, minerals, and complex organic compounds. Roughly 50% of a comet's mass is water ice, while the rest includes rock-forming elements and organic material. These components are strikingly similar to those found on Earth, suggesting a shared cosmic origin. To better understand comets, planetary scientists have even recreated them in laboratories. The recipe for building a comet involves starting with dry ice to represent frozen carbon dioxide. Add dirt to mimic rock-forming elements, water for the ice, and even methanol and ammonia, often found in window cleaners, to simulate the minor icy compounds in real comets. For a touch of creativity, scientists sometimes include chocolate sauce, representing the tar-like organic materials found in comets. Gravity does the rest, packing the materials together to form a crude but accurate model of a comet. In 1985, NASA discovered water inside Halley's Comet during a groundbreaking mission. Comets, predominantly composed of water ice, carry the very liquid that sustains life on Earth. As the bombardment waned and Earth's surface began to cool, it's believed that later comet impacts delivered water to the planet. This water vaporized on impact, condensed in the atmosphere, and eventually rained back down, forming pools and lakes on the cooling surface. However, some scientists argue that comets alone may not have been the sole contributors to Earth's water supply. If that's the case, where did the rest come from? For decades, astronomers speculated about the existence of another reservoir of comets closer to the inner solar system than the Oort cloud. In the mid-20th century, American astronomer Gerard Kuiper proposed the existence of a vast region of icy bodies beyond Neptune. This hypothetical region, now known as the Kuiper Belt, remained unproven until 1992, when astronomers discovered the first Kuiper Belt object. This discovery revolutionized our understanding of the solar system. No longer did the solar system end at Neptune or Pluto. Instead, it extended into a new frontier filled with hundreds of thousands of icy objects. These objects, known as short-period comets, are much closer to the inner solar system than their long-period counterparts from the Oort cloud. Short-period comets typically orbit the Sun in less than 200 years, making them more accessible for study. The Kuiper Belt is thought to contain as many as 100,000 comets, with some measuring up to 600 miles across, larger than New York City. These icy giants, scattered billions of miles beyond Neptune, are a treasure trove for understanding the dynamics of the solar system. The Kuiper Belt has fundamentally changed how we view the architecture of the solar system. These icy remnants from the formation of the planets provide a bridge between the inner and outer reaches of our cosmic neighborhood. They are not just relics of the past. They are active participants in shaping our understanding of planetary science, water delivery, and even the origins of life itself. Calculations reveal that the modern-day Kuiper Belt is but a shadow of its former self. When it first formed, this region of icy bodies held 100 times more objects than it does today, making it an abundant source of water-carrying comets. Astonishingly, even now, Kuiper Belt comets continue to deliver material to Earth. While the era of violent bombardment has long passed, comet dust rains down on our planet continuously. As Earth moves through the solar system, it sweeps through the particle tails of comets. Larger debris burns up as fiery streaks in our atmosphere, but smaller particles survive, falling to the surface as space dust. To scientists, this dust is more than just debris. It is a treasure trove of information. Encased within these particles is a record of how the Sun, Earth, and other planets formed. However, there's a significant challenge. When comet dust interacts with Earth's atmosphere, its chemical composition changes, erasing the pristine record of the early solar system. Scientists realized that the only way to fully understand this material was to collect uncontaminated samples directly from a comet in space. In the late 1990s, NASA's Stardust mission was born. It was an ambitious idea: travel to a known comet, collect dust particles, and return them safely to Earth. For one of the project's lead scientists, Mike Zelensky, the mission was a once-in-a-lifetime opportunity. To actually be able to go to a known comet, grab a sample, and bring it back to Earth. It was just a fantastic prospect, he explained. The mission's target was Comet Wild 2, a Kuiper Belt comet measuring over 3 miles wide and traveling at 13,000 miles per hour. To capture the speeding dust without destroying it, NASA developed an innovative material called aerogel, a lightweight, glass-like substance capable of cushioning the particles upon impact. This aerogel was mounted onto a tennis racket-shaped paddle extending from the spacecraft. Launched in February 1999, Stardust embarked on a 3 billion-mile journey to rendezvous with Wild 2. The spacecraft had to make 3 orbits of the Sun and perform a gravitational slingshot maneuver past Earth to align its trajectory with the comet. The journey took 5 years of meticulous navigation and planning. But in January 2004, Stardust finally approached Wild 2. The team at Mission Control faced a delicate balance. Passing too close to the comet risked destroying the spacecraft with debris, while passing too far would result in insufficient sample collection. In a tense moment, Stardust flew within 150 miles of the comet's nucleus, close enough to extend its aerogel collector into the stream of particles erupting from Wild 2. For the next several minutes, the paddle was bombarded with speeding particles. Despite the intense activity, Stardust successfully captured the precious dust samples. With its primary mission complete, the spacecraft began its long journey back to Earth. 2 years later, in January 2006, Stardust's return capsule entered Earth's atmosphere. Streaking across the night sky as a brilliant fireball, it was closely monitored by NASA scientists. The capsule landed safely in the Utah desert, and the mission team carefully transported it to a secure laboratory. The moment of truth came when the capsule was opened. At first, the sample appeared so clean that scientists feared the mission had failed. But as they examined the aerogel under powerful microscopes, tiny impact craters became visible, confirming that the mission had worked. At NASA's Johnson Space Center, researchers began analyzing the comet dust with advanced tools, including electron microscopes. Mike Zelensky likened the process to forensic detective work. We're looking at tiny little clues to understand how the planets were born, how the sun formed, and even what existed before that. It's just like being a detective. The samples contained superheated grains, which must have formed close to the sun in the solar system's earliest days. These grains had somehow been transported billions of miles to the far reaches of the Kuiper Belt, a discovery that shed new light on the dynamic processes shaping the solar system. By studying these grains, scientists confirmed that comets are not static relics, but active participants in the solar system's evolution. They transport materials from one region to another, shaping planets and possibly delivering the building blocks of life. In 1999, NASA embarked on one of its boldest missions yet, one that seemed straight out of a Hollywood blockbuster. Named Deep Impact, the mission aimed to do something unprecedented: collide with a comet to reveal its hidden interior. As principal investigator Mike A. Hearn explained, comets are a preserved record of what happened 4.5 billion years ago. Unfortunately, that record has been disturbed on the surface layers of comets, and you have to get down to the interior to understand what the data really are in the time capsule. The target was Comet 9P/Tempel-1, a short-period comet approximately 9 miles wide. The plan was ambitious. NASA would launch a spacecraft carrying a 1-ton copper projectile designed to slam into the comet's nucleus at 23,000 miles per hour, creating a crater over 400 feet wide and 40 feet deep. The collision was expected to eject pristine organic material buried deep inside, material that had been preserved since the formation of the solar system. Executing this mission was a feat of incredible precision. Deep Impact had to not only reach the comet's orbit, but also ensure that it arrived at the exact point where the comet would be at the right time. This was akin to two people standing on opposite sides of the Earth, shooting bullets, and having them collide perfectly in midair. In January 2005, Deep Impact launched from Cape Canaveral, beginning its journey through space. As it approached the comet over the following months, anticipation grew among the scientists at Mission Control. On July 4, 2005, the probe's projectile successfully collided with Tempel-1 at the planned velocity. The team erupted in celebration. First thrilled, then scared. 6 years of my life for any reason gone wrong. But it worked just beautifully. Everything was fine. It's a crowning achievement. It really makes you feel wonderful, one scientist remarked. The collision generated a massive explosion, ejecting thousands of tons of fine dust particles into space. While this was a testament to the force of the impact, it also posed an unforeseen challenge. The thick cloud of dust obscured the newly formed crater, making it impossible for scientists to directly observe the pristine materials buried within the nucleus. The biggest disappointment was that the material came out in such fine particles that we couldn't see through it, Ahern admitted. If the material had come out with a lot of big chunks, it would have been relatively transparent. Despite this setback, the mission yielded valuable insights. The comet's weak gravitational pull meant that if a person stood on its surface, they would weigh less than a gram and could literally jump into orbit. The structure of the nucleus was astonishingly fragile, comparable to the texture of lemon meringue, revealing that comets are far less solid than previously thought. Imagine a comet just 1 mile wide colliding with Earth. Traveling at over 100,000 miles per hour, it would rip through the atmosphere in mere seconds, triggering a catastrophe of unimaginable scale. The initial impact would kill millions, but the true devastation would come from the chain reaction of disasters that follow. Massive earthquakes would shake the planet, and tsunamis would surge deep inland, obliterating entire regions. Fires would consume cities, and a dense cloud of dust would envelop the Earth, blocking out sunlight. Within weeks, the death toll would rise to hundreds of millions. Without clean water, food, or electricity, humanity would face a grim reality. The planet would descend into a nuclear winter, and within a year, much of the Earth's population could be wiped out. It's a chilling thought, but one that scientists say is not a question of if, but when. Fortunately, Earth has an unlikely ally in the battle against these cosmic threats: Jupiter, the solar system's giant guardian. With a mass 320 times greater than Earth, Jupiter's immense gravitational pull acts as a shield, redirecting or capturing comets that might otherwise head toward our planet. In 1992, the world witnessed Jupiter's protective power when the planet intercepted Comet Shoemaker, Levy 9. As the comet passed too close to Jupiter, its gravity tore the icy body into 21 fragments, sending them plunging into its atmosphere at speeds of 35 miles per second. The impacts were staggering. Each fragment drilled through Jupiter's atmosphere, exploding with immense energy and sending debris shooting back into the atmosphere. The resulting scars were larger than Earth. The most powerful strike came from a fragment 2 miles wide, unleashing an energy equivalent to 6 million megatons of TNT, about 600 times the combined power of Earth's nuclear arsenal. This event was a stark reminder of the fragility of life on Earth. If such a collision were to happen here, the consequences would be catastrophic. Although major impacts on Earth are rare, history shows that they still occur. In 1972, a small object skimmed along the Earth's atmosphere before bouncing back into space. If it had penetrated further, it could have destroyed a city. The people of Tunguska, Siberia, were not so fortunate. On the morning of June 30th, 1908, a mysterious object, likely a comet or asteroid, exploded just 3 miles above the ground. The explosion released energy equivalent to 1,000 Hiroshima bombs, flattening over 60 million trees across an area 12 times larger than Washington, D.C. Miraculously, only a small number of people were killed due to the remote location. However, had the Tunguska event occurred over a major metropolitan area, the devastation would have been incomprehensible. If Jupiter fails to shield us from a catastrophic comet, humanity will need to take action. Advances in space technology, such as early detection systems and potential methods to deflect or destroy incoming objects, are our best hope. Missions like NASA's DART, designed to test planetary defense strategies, are a promising start. NASA's Near-Earth Object Program stands as Earth's first line of defense against potentially catastrophic impacts from space. Established in 1998, this program aims to discover, catalog, and monitor the movements of comets and asteroids that could pose a threat to our planet. Managed by Don Yeomans, the program relies on 5 observatories and a global network of astronomers who scan the skies 24/7, searching for these celestial wanderers. It's what we call a low-probability, high-consequence event, Yeomans explains. These impacts don't happen often, thankfully, but when they do, the results are catastrophic. So, it makes sense to have some insurance against them. Astronomers identify potential threats by taking multiple photographs of the same region of space over time. A computer scans these images, detecting any object that moves against the static backdrop of stars. Once a moving body is located, its orbit is calculated to determine if it poses a risk to Earth. If a comet or asteroid is found to be on a collision course, several methods have been proposed to prevent disaster. One idea is to destroy it with a nuclear weapon, but this approach carries risks. If the object isn't completely deflected, the remaining fragments could still hit Earth, now radioactive, making the disaster even worse. One of the greatest challenges in comet defense is early detection. Comets are notoriously difficult to spot because their surfaces are darker than charcoal. They only become visible as comets when they are close to the Sun, inside the orbit of Jupiter, giving Earth just a few months to respond. Would we be ready to stop a planet-killing comet with only 3 months' warning? For now, the answer is no. While programs like the Near-Earth Object Program focus on prevention, missions like Rosetta, operated by the European Space Agency, aim to deepen our understanding of comets. Named after the Rosetta Stone, which unlocked the secrets of ancient Egyptian hieroglyphs, the Rosetta mission seeks to decode the mysteries of comets and their role in the formation of the solar system. Launched on a 4.4 billion-mile journey, Rosetta's target is Comet Churyumov-Gerasimenko, a short-period comet orbiting the Sun. After over a decade in space, Rosetta reached the comet in 2014 and released a small probe onto its surface. For a week, this probe conducted groundbreaking experiments, including taking photographs and analyzing the chemical composition of the comet's ice and dust. The data was then relayed back to the satellite for further analysis. Unlike previous missions that merely observed comets from a distance, Rosetta worked like a geologist, not just looking at the surface, but probing deeper, examining the structure and composition of the comet in detail. This hands-on approach has the potential to revolutionize our understanding of these ancient bodies. Comets may not only hold answers to humanity's past, but could also be key to its future. As Rosetta continues its mission, scientists are beginning to envision a future where comets serve as stepping stones for interplanetary exploration. If we're going to build habitats in space, we'll need water, explains a planetary scientist. Comets are rich in water ice, and if we break that down into hydrogen and oxygen, we get the most efficient type of rocket fuel. This vision positions comets as fueling stations for humanity's expansion into the cosmos. By mining their resources, we could create sustainable outposts on distant worlds, enabling deeper exploration of our solar system and beyond. Over the last 2 decades, missions like Giotto, Stardust, Deep Impact, and Rosetta have vastly expanded our understanding of comets and their significance in the solar system. They've shown us that comets are not just threats, but also clues to our origins and potential allies in humanity's survival. Yet, as we search for answers to profound questions, how the solar system began, whether Earth is unique, and what humanity's future holds, we must also grapple with the possibility that one of these ancient travelers could end our story entirely. The irony is not lost. Without comets, there may never have been life on Earth, yet one day, a comet may wipe that life away. Whether as messengers of the past resources for the future, or existential threats, comets challenge us to understand, prepare, and adapt. Our survival may ultimately depend on how well we heed their lessons. Leaving the icy mysteries of comets behind, we now journey to one of the most mesmerizing and enigmatic planets in our solar system, Saturn. Known for its dazzling rings and countless moons, Saturn holds secrets that could reshape our understanding of planetary science and the possibilities of life beyond Earth. Let's uncover them. Cassini. Unlocking Saturn's Secrets. On October 15, 1997, the Cassini-Huygens spacecraft embarked on an extraordinary journey to Saturn, launching aboard an 1,100-ton Titan IVB rocket from Cape Canaveral. This was no ordinary mission. Saturn, lying nearly 900 million miles away, had not been visited by a spacecraft in over 25 years. The planet, with its iconic rings and over 60 moons, is a massive gas giant, more than 750 times the mass of Earth, and lacks a solid surface. The last mission to Saturn, conducted by the Voyager spacecraft, revealed tantalizing glimpses of this distant world. Images showed thick, banded clouds swirling in the planet's atmosphere, and infrared cameras detected signs of storm activity beneath the haze. But Voyager's mission was limited. It was a flyby, capturing only fleeting snapshots as it sped past at thousands of miles per hour. Scientists were left with far more questions than answers. Voyager 1's brief encounter with Saturn's largest moon, Titan, was especially intriguing. Its instruments detected organic compounds in Titan's atmosphere, compounds similar to those that formed the building blocks of life on Earth 4 billion years ago. Scientists saw Titan as a time capsule, offering a glimpse into the chemical processes that may have led to life on our own planet. Yet, like with Saturn itself, Voyager 1 had no opportunity to linger. At a velocity of 39,000 miles per hour, it hurtled away into the outer solar system, leaving behind a trail of unanswered questions. The discoveries made by Voyager inspired a new mission, one that could delve deeper into Saturn's mysteries and those of its enigmatic moon, Titan. We want to understand our own origins, scientists explained. Why did Earth become what it is? How did life emerge here? By studying Saturn and its moons, they hope to unlock answers to these profound questions. Cassini was a technological marvel, one of the most advanced spacecraft ever built. Equipped with an array of high-tech cameras and sensors, it was designed to study Saturn's atmosphere, rings, and moons in unprecedented detail. Alongside it traveled Huygens, a small probe destined to explore Titan. The probe was engineered to descend through Titan's dense atmosphere and land on its surface, making history as the first human-made object to do so. Reaching Saturn, however, was no small feat. The mission required navigating a 2 billion-mile journey through the solar system. To conserve fuel, Mission Control used the gravitational pull of nearby planets as a slingshot, propelling the spacecraft through a series of flybys around Venus, Earth, and Jupiter. This clever use of gravity gave Cassini the momentum it needed to reach its distant destination. After 7 years of travel, Saturn finally loomed into view. The spacecraft began sending back images of the gas giant, each one more stunning than the last. Saturn's ethereal rings, composed of billions of ice particles, shimmered against the darkness of space. But before Cassini could begin its detailed exploration, it faced a harrowing challenge. It had to pass through the rings themselves. The rings of Saturn, while breathtaking, are also perilous. Stretching over 170,000 miles, they are composed of particles ranging in size from tiny grains of dust to chunks as large as a house. Any collision with these particles could prove catastrophic for the spacecraft. Cassini's team meticulously calculated its trajectory, navigating through a gap in the rings where the risk of collision was minimal. As Cassini threaded its way through this celestial obstacle course, its instruments captured the most detailed images of Saturn's rings ever seen. The spacecraft revealed the complexity of their structure. Dense bands interspersed with gaps and delicate wave-like patterns caused by the gravitational pull of Saturn's moons. With this successful maneuver, Cassini had overcome its first major hurdle. Now, the spacecraft was ready to begin its historic exploration of Saturn. A mission that would last 13 years, transforming our understanding of this majestic planet and its mysterious moons. Cassini's journey was just beginning, and the secrets it would uncover would astonish scientists and reshape our knowledge of the solar system. Saturn's rings, while breathtakingly beautiful, are a chaotic and perilous maze. Made up of billions of particles of ice and rock whizzing around the planet at high speed, they include fragments as large as houses. For Cassini to reach its destination, it had to navigate a narrow gap between the rings, a maneuver fraught with risk. As Cassini approached, the tension at mission control was palpable. Dr. Jeff Kuzi, overseeing the spacecraft's entry, described the gap as something you wouldn't see with your eye, emphasizing the precision needed for the task. It was like threading a needle across 900 million miles of space. Cassini fired its rocket engines to align its trajectory and aimed for the gap. To shield itself from potential damage, the spacecraft turned its antenna away from Earth, cutting off communication during this critical phase. All the team could do was wait. Dr. Larry Esposito, part of the mission team, described the anticipation as excruciating. Everyone was holding their breath, waiting for the signal to come from the spacecraft. Hours passed before Cassini's signal finally returned. It had successfully navigated the ring plane. Relief swept through mission control, giving way to cheers, handshakes, and even tears. After decades of planning and 7 years of travel, Cassini had become the first spacecraft to enter orbit around a planet in the outer solar system. With Cassini safely in orbit, the mission's true work could begin. For the first time, a spacecraft had the opportunity to observe Saturn up close for years, capturing data from multiple perspectives. Dr. Tony Del Genio celebrated this historic milestone. The beauty of the Cassini mission is that, for the first time, we get to go into orbit around a planet like Saturn and, for years, observe it over and over again from different angles. Finally, some of the secrets start to be revealed to us. Cassini's first task was to explore Saturn's thick atmosphere. Maneuvering toward the South Pole, it made a startling discovery: a massive hurricane-like vortex, unlike anything ever observed outside Earth. This monstrous storm, more than 1,000 miles wide, dwarfs hurricanes on Earth. Its eye is encircled by a towering wall of clouds, rising an astonishing 45 miles high. while winds roar at 350 miles per hour. Temperatures in the upper layers of the storm plummet to minus 167 degrees Fahrenheit, creating flurries of ice crystals that Cassini's cameras captured in stunning detail. The storm's scale and behavior mirrored hurricanes on Earth, with swirling clouds and a defined eye. But its size and power were uniquely Saturnian, a testament to the extremes of this gas giant. Cassini's journey through Saturn's orbit was just beginning, but even in these early moments, it had already transformed humanity's understanding of this distant world. For the first time, Saturn was not just a shimmering light in the sky, but a dynamic, complex planet with secrets waiting to be unraveled. Decoding Saturn's storms. The power within Saturn's immense swirling storms have captivated scientists. Like Earth's hurricanes, they feature swirling clouds, powerful winds, and even snow. "It definitely snows on Saturn," one scientist noted. In the upper reaches of these storms, large ice crystals form and fall, while deeper within, hidden from view, liquid water rain likely pours out of the storm clouds. But what powers these colossal tempests? Unlike Earth, where hurricanes are fueled by the sun's energy and warm ocean waters, Saturn is far too distant from the sun to draw enough energy for its massive storms. The mystery lies deeper within the planet itself. Saturn, a gas giant, has no solid surface to slow its winds. Once a storm starts, it can persist for long periods, circulating energy across the atmosphere. Still, without a continuous energy source, even these winds would eventually dissipate. Many scientists believe that the energy fueling Saturn's storms comes from deep inside the planet. Driven by heat left over from Saturn's formation and the gravitational compression of its massive layers. Cassini captured mesmerizing images of Saturn's most powerful storms, including a hurricane-like vortex at the planet's south pole, where winds roared at over 350 miles per hour. The storm's sheer scale, a swirling tempest 2/3 the size of Earth, left scientists in awe. But while its intensity was clear, its energy source remained elusive. In the Coriolis laboratory in France, astrophysicist Peter Reed set out to test the theory that internal heat drives Saturn's storms. Using an innovative experiment, Reed sought to recreate the turbulent atmosphere of the gas giant in a controlled environment. At the heart of the experiment was a giant rotating tank containing nearly 40,000 gallons of fluid. The fluid acted like Saturn's gaseous atmosphere, while a heater at the base of the tank simulated the internal heat radiating from the planet's core. To mimic the behavior of Saturn's clouds, light-sensitive particles were suspended in the fluid. These particles, carried by the artificial winds, allowed scientists to visualize the currents and vortices forming in the tank. The tank was set spinning to emulate Saturn's rotation. As the fluid moved, the tiny particles began to interact, creating swirling patterns reminiscent of Saturn's jet streams and storm bands. Slowly but surely, the particles organized into eastward and westward jet streams, with distinct vortices forming, just like the stormy bands observed on Saturn's surface. The experiment demonstrated that internal heat combined with the planet's rapid rotation could organize atmospheric patterns into the banded structures and powerful jet streams seen on Saturn. "We can see evidence of a jet structure," Reed remarked, pointing to the fluid in motion. "And here we can see a very nice rotating structure." While the experiment didn't provide all the answers, It offered strong support for the theory that heat from Saturn's interior drives its colossal storms. These findings bring scientists closer to understanding the mechanics of gas giant atmospheres, not just on Saturn, but on other planets like Jupiter and Neptune as well. As Cassini continued its mission, the insights from experiments like these gave researchers new tools to interpret the spacecraft's findings, unraveling more of Saturn's secrets and reshaping humanity's understanding of planetary science. The hidden power of Saturn's core. Saturn's anticyclonic vortices, with their swirling patterns of clouds, continue to amaze scientists. Experiments like Peter Reed's have hinted that a heat source deep within the planet fuels its monstrous storms. But what exactly lies at Saturn's core to generate such immense energy? Saturn, composed of approximately 75% hydrogen and 25% helium, with traces of methane, water, and ammonia, is a gaseous world. Yet, scientists believe it hides a hot, rocky core, roughly the size of Earth, surrounded by extreme pressure zones that hold the key to its energy. On Earth, internal heat comes from the radioactive decay of materials in the core and residual heat from its formation. But in Saturn, heat generation operates on a different scale. Near its core, the pressure is so immense, millions of times greater than on Earth's surface, that hydrogen and helium gases are compressed into metallic liquids. If you get deep enough, one researcher explains, the hydrogen and helium become so dense that they don't behave like gases anymore. They act like electrically conducting metals. These liquids swirl around Saturn's rocky core, but they do not mix. The heavier helium sinks through the hydrogen, creating friction and releasing heat in the process. This mechanism may explain why Saturn emits 3 times more heat into space than it receives from the Sun. To investigate further, Cassini has been collecting precise measurements of helium levels in Saturn's atmosphere, providing vital clues to this dynamic process. The data is so extensive that it will take years to analyze, but scientists are optimistic about uncovering the secrets of Saturn's internal energy. Cassini's mission now shifts outward to examine one of Saturn's most iconic features: its spectacular rings. These rings, first revealed in detail by the Voyager missions over 25 years ago, remain the largest and most dynamic in the solar system. Composed of billions of chunks of ice and rock, Saturn's rings resemble a turbulent boulder field, with particles ranging in size from mere fractions of an inch to several yards across. The constant collisions between these fragments create an ever-shifting landscape of chaos and beauty. If you were to fly over the rings very close, you'd see something that looks like a flying boulder field, a scientist remarked. The rings' turbulent activity sparked an intriguing question. Could the processes shaping them mirror the formation of planets in the early solar system? Over 4.5 billion years ago, a similar disk of gas and dust encircled the young Sun. As particles clumped together over millions of years, they grew larger, eventually forming the planets we see today. Cassini's high-resolution images of Saturn's rings offer a stunning glimpse into this analogy. The detailed snapshots show particles aggregating, hinting at the same mechanisms that might have operated in the protoplanetary disk of the solar system's infancy. I was very, very excited to see these beautiful, beautiful images, one mission scientist shared, reflecting the awe Cassini inspires. By studying Saturn's rings, scientists gain a unique window into the processes that shaped our solar system billions of years ago. Cassini's findings suggest that the same forces acting within the rings today may have sculpted the planets in the distant past. As the spacecraft continues its journey, its discoveries are not only redefining our understanding of Saturn, but also offering a glimpse into the cosmic forces that shaped the very world we call home. Cassini's revelations, Saturn's rings, and the mystery of Titan. Cassini's exploration of Saturn's rings provided scientists with some of the most detailed images ever captured, transforming their understanding of these celestial structures. Using an ultraviolet imaging spectrograph, Cassini mapped the intricate structure of the rings with astonishing clarity. The spectacular detail we saw was an eye-opener, one scientist remarked. As particles in the rings passed in front of distant stars, the UV spectrograph measured the amount of starlight that filtered through. Areas with dense particle concentrations blocked the starlight, appearing darker, while less dense regions allowed more light to shine through. The darker regions revealed fascinating structures called moonlets, temporary clumps of particles that appeared as bright lumps in Cassini's images. Scientists believe these moonlets are aggregations of smaller particles, held together by gravity and surface stickiness. These big boulders may be nothing but an agglomeration of smaller ones, a researcher explained. As they bump into each other, they may collapse and fall apart, only to reform over time. This discovery fascinated scientists, as it echoed the processes that shaped the early solar system. Over billions of years, microscopic specks of dust interacted and clumped together to form the planets. The interaction between the moonlets and the ring particles is exactly like the interactions between a planet and the dust collecting to make that planet grow, one researcher observed. Cassini's images offered unparalleled insight into the mechanisms of planetary formation, providing a glimpse into how our solar system and our world came to be. Despite their grandeur, the origin of Saturn's rings remained a mystery. Scientists hypothesized that they formed during the solar system's violent early years, when comets and asteroids frequently collided with young planets, creating explosive impacts and leaving scars that endure to this day. Saturn's moon Mimas illustrates the destructive power of these collisions. A massive crater dents its surface, a scar from a catastrophic impact that the moon narrowly survived. But other moons may not have been so lucky. Scientists believe that one of Saturn's ancient moons could have been shattered during a collision, breaking apart into billions of fragments. Saturn's immense gravity likely captured these fragments, compressing them over time into the flat, luminous plane of icy particles that now encircle the planet. These rings, born from destruction, offer a window into the solar system's turbulent infancy. As Cassini completed its study of Saturn's rings, its next target was Titan, Saturn's largest moon and one of the most enigmatic worlds in the solar system. Titan is massive, weighing nearly twice as much as Earth's moon, and its thick orange atmosphere has puzzled scientists for decades. In 1980, Voyager 1 sent back the first images of Titan. Shrouded in haze, the moon's surface was hidden beneath its dense atmosphere. The presence of organic compounds suggested that Titan's environment might mirror that of early Earth, offering scientists a unique opportunity to study processes that could have led to the development of life. To explore this mysterious moon, Cassini carried a secondary probe called Huygens, designed specifically to land on Titan's surface. With this mission, scientists hope to peer beneath the haze and uncover the secrets of a world frozen in time. A glimpse into Earth's past before life began. Having crossed over 2 billion miles of space, Cassini and Huygens were poised to deliver groundbreaking discoveries, unlocking not just the mysteries of Titan, but also clues to the evolution of planets and the origins of life itself. As the spacecraft approached this intriguing moon, anticipation reached a fever pitch. Titan, a world unlike any other, awaited exploration. Titan, a world like no other Titan, Saturn's largest moon, holds an atmosphere strikingly similar to that of early Earth. Composed primarily of nitrogen, it also contains water vapor and traces of organic compounds like ethane and carbon dioxide, key ingredients that could potentially serve as the raw materials for life. For scientists, Titan offers a glimpse into Earth's distant past, making it one of the most intriguing destinations in the solar system. The Huygens probe, carried by Cassini, was tasked with solving the mystery of what lies beneath Titan's thick orange haze. Dr. Carolyn Porco, who had worked on the Voyager mission decades earlier, expressed the immense anticipation among scientists as Cassini returned to the Saturn system. You can imagine the excitement of coming back to study a place that had captivated us 24 years earlier. Cassini's cameras alone couldn't fully penetrate Titan's dense atmosphere, leaving its surface obscured and enigmatic. Early images painted a mystifying picture, hinting at an alien world but revealing little detail. To uncover the secrets beneath the haze, the Huygens probe plunged into Titan's atmosphere at over 13,000 miles per hour. At first, Huygens cameras transmitted only images of thick yellow haze, making the descent seem like a journey into the unknown. But at around 30 miles above the surface, the haze began to clear, and Titan's landscape came into focus. The first images revealed a desert-like terrain of low hills and rolling plains, an alien world unlike anything seen before. Dr. Ralph Lorenz, a mission engineer, shared the team's anxiety about where Huygens would land. "We didn't know if it would survive. It could have landed in a lake of liquid hydrocarbons, on ice, or even a sand dune." To everyone's relief, Huygens touched down on level ground and survived. It became the first probe to land on another world in the outer solar system. Huygens's onboard cameras and instruments revealed an eerie alien landscape. A penetrometer, designed to measure the texture of the surface, detected ground with the consistency of damp sand or soft clay, possibly with a crust on top. Lorenz joked, "It was like crème brûlée." The most astonishing discovery came from the camera's images, which showed smooth, rounded pebbles scattered across the surface. These pebbles resembled those found in Earth's riverbeds, suggesting that they had been tumbled in flowing liquid. The surrounding area, marked by river gullies, indicated that rain had once fallen on Titan, carving channels and washing down these rocks. Huygens's findings provided the first unambiguous signs of liquid activity on Titan's surface. A groundbreaking revelation. The discovery of a riverbed posed another question. What liquid could have carved it? Huygens's instruments measured Titan's surface temperature at a frigid 290 degrees Fahrenheit below zero, far too cold for liquid water. At such temperatures, water would be as solid as rock. The answer lay in Titan's unique climate. Instead of water, liquid methane and ethane, hydrocarbons that remain liquid in Titan's bitter cold, likely flowed across its surface, carving the riverbed and creating the smooth pebbles observed by Huygens. As Huygens continued to probe from the ground, Cassini shifted its focus to Titan's uncharted North Pole. Using radar to penetrate the dense smog, Cassini uncovered a startling discovery. Dark patches scattered across the region. These patches, invisible in optical wavelengths, suggested something astonishing: large bodies of liquid. Titan's North Pole appeared to host seas and lakes of liquid methane and ethane, providing further evidence of a dynamic, alien world shaped by flowing hydrocarbons. Huygens and Cassini together unveiled a Titan that is both eerily familiar and profoundly alien. With an atmosphere resembling early Earth and evidence of liquid activity on its surface, Titan offers a unique laboratory to study processes that could one day lead to life. As Cassini continued its exploration, Titan's secrets began to unfold, shedding light not just on this mysterious moon, but on the origins of Earth and the potential for life elsewhere in the universe. Titan remains a testament to the power of exploration and humanity's relentless quest to understand our place in the cosmos. Titan, Saturn's largest moon, continues to astonish scientists with its alien yet familiar features. Its surface, shaped not by water, but by liquid methane, offers a fascinating glimpse into an otherworldly hydrological cycle. While temperatures on Titan plunge far below freezing, making water as solid as rock, methane remains liquid, flowing across the surface and carving riverbeds, gullies, and lakes. Cassini's visual and infrared mapping spectrometer captured dramatic images of a massive cloud system engulfing Titan's North Pole. These clouds, composed of methane, appear to supply the liquid filling the moon's lakes. "We've counted up the volume of liquid in some of these lakes," a scientist noted, "and it's hundreds of times the amount of all the liquefied natural gas and oil on Earth." This methane-based hydrological system operates similarly to Earth's water cycle, with evaporation, cloud formation, and precipitation. But Titan's surface conditions, with frigid temperatures and frozen water, are inhospitable to life as we know it. If Titan's surface seems unwelcoming, its atmosphere tells a different story. Scientists are captivated by the tiny particles suspended in its nitrogen-rich skies, first discovered decades ago by Voyager. These particles are a cocktail of organic molecules, the same kind of substances that existed on Earth 4 billion years ago, when life was beginning to take shape. Understanding how these molecules form on Titan could unlock the secrets of how life developed on Earth. Cassini's instruments isolated the exact mix of these molecules and transmitted the data back to mission control. Astrobiologist Dr. Chris McKay, who had spent years simulating Titan's atmosphere in the lab, was thrilled by the findings. "As soon as the Cassini results came in, we scrambled to adjust our experiments," McKay explained. "It was like seeing the answer at the back of the book after working on a problem for a decade." McKay recreated Titan's environment in his lab, simulating its pressure, temperature, and methane-rich atmosphere. A mixture of methane and nitrogen was passed through a reaction chamber where an electric discharge simulated the sun's ultraviolet radiation. "This is Titan in a jar," McKay said, as the experiment replicated Titan's atmospheric processes. Within hours, Simple molecules like methane and nitrogen transformed into complex nitrogen-rich compounds called tholins. These substances, which Cassini had detected on Titan, resemble the precursors of life's building blocks on Earth. The tholins produced in McKay's lab were nearly identical to those found on Titan, offering a unique opportunity to study the chemistry that might lead to life. One of the big questions is whether the chemistry that led to life on Earth is a rare, unique process or a common occurrence on planets like Earth, or even moons like Titan, McKay remarked. If Titan's processes mirror those of early Earth, it suggests that life might not be unique to our planet. Instead, the steps that lead to life, organic chemistry, energy input, and the right environmental conditions might be commonplace in the universe. Cassini's exploration of Titan shows how life could emerge on other worlds, offering hope for discovering life beyond Earth. After more than 3 hours of groundbreaking data collection and 750 stunning images, Huygens' batteries finally died out. Its landing on Titan marked one of the most significant achievements in the history of space exploration. The probe provided humanity with its first close-up look at a moon that could hold clues to the origins of life itself. As Huygens' mission concluded, Cassini continued its journey, leaving Titan behind to explore another of Saturn's enigmatic moons, Enceladus. This icy world, with its hidden subsurface ocean, promised even greater revelations about the potential for life in our solar system. With every discovery, Cassini reaffirmed the importance of exploration, revealing the extraordinary possibilities that lie beyond our home planet. The surprising secrets of Enceladus. As Cassini continues its exploration of Saturn's moons, it turns its attention to the icy and enigmatic Enceladus, one of the brightest objects in the solar system. Cassini's cameras capture breathtaking images of this frozen moon, revealing a surface marked by fractured plains, craters, and folded mountains. Enceladus is a dazzling world, but beneath its icy exterior lies an even greater mystery. During a close flyby, Cassini's magnetometer detects a peculiar disturbance in Saturn's immense magnetic field. The moon appears to be emitting gas, suggesting the presence of a tenuous atmosphere. This discovery is unexpected. Enceladus is just 300 miles across, far too small and with insufficient gravity to retain an atmosphere for long. Initially, planetary scientists, including Professor Bob Brown, were skeptical. "An object like this can't have an atmosphere," Brown remarked. But as the data continued to flow in, the mystery deepened. Cassini's instruments revealed that the atmosphere-like phenomenon was concentrated around Enceladus's south pole. Such a localized atmosphere defied conventional understanding. Atmospheres should be distributed uniformly around a celestial body. Determined to uncover the source of this anomaly, Cassini moved closer to Enceladus. What it found was astonishing. Giant geysers at the South Pole erupting into space, launching massive plumes of vapor over 400 miles high. The sight of the jets left scientists in awe. It was one of those discoveries that happens once in a lifetime, a team member recalled. Using its spectrograph, Cassini analyzed the composition of the vapor. The results were mind-blowing. The plumes contained water. The implications were profound. Could liquid water, a critical ingredient for life, exist beneath the icy crust of this tiny moon? Cassini zeroed in on the cracked terrain at Enceladus's south pole, an area that appeared to hold the key to the geysers. These regions were far warmer than expected, with temperatures potentially reaching 0 degrees Celsius, warm enough to allow liquid water to exist just below the surface. This discovery was as puzzling as it was exciting. "It's one thing to find a warm body," a scientist explained. "But it's entirely different to find that it's warm only in one location." The heat appeared to be confined to the cracks, suggesting an internal heat source driving the activity. Enceladus, once thought to be a frozen and inert world, now seemed alive with dynamic processes. The localized warmth and water-rich plumes hinted at the possibility of a subsurface ocean, raising questions about the moon's potential to support life. For Cassini, this discovery marked the beginning of a new chapter, transforming Enceladus from a small, icy satellite into one of the most exciting destinations in the solar system. Enceladus, a world of possibilities. The discovery of localized warmth and water-rich plumes on Enceladus has left scientists scrambling to understand what generates these pockets of heat. One prevailing theory centers on the moon's elliptical orbit around Saturn. As Enceladus moves closer to the planet, tidal forces flex its icy crust, creating friction at fault lines. When it moves farther away, the crust relaxes. This continuous flexing generates heat, possibly enough to melt the ice within the faults. Enceladus flexes its body, and that can produce friction enough to melt ice, to create liquid water, one researcher explained. The prospect of liquid water on this frozen moon demands further exploration. To uncover the secrets of Enceladus's plumes, NASA directed Cassini to fly just 30 miles above the moon's surface, passing directly through the jets of vapor erupting from the South Pole. The spacecraft's instruments analyzed the plume's composition, and the results were astonishing. The plumes contained water vapor, nitrogen, and simple organic molecules. These ingredients, water, heat, and organic chemistry, are the fundamental components needed to support life. It doesn't take much of a jump at that point to make the association, a scientist remarked. If you have water, heat, and organic chemicals, you have the conditions that might actually produce primitive life. The evidence suggests that beneath Enceladus's icy crust lies a subterranean sea, possibly connected to the surface through deep faults. This dark, sunless world could still harbor life. On Earth, similar environments exist at hydrothermal vents on the ocean floor. These vents, which spew hot, mineral-rich water, support thriving ecosystems of primitive organisms despite the extreme conditions. There's the possibility of having something akin to those hydrothermal vents that we see at the bottom of the ocean, a scientist noted. And we know there are living organisms there. If life exists on Enceladus, even in its simplest forms, the implications would be profound. What could be a more important scientific discovery than to find out life has evolved separately in some other place? A researcher asked. That changes the whole picture for human beings. If scientists can confirm that life originated independently on Enceladus, it would suggest that the processes leading to life are not unique to Earth. Such a discovery would break the notion of Earth's exclusivity, implying that life could be common throughout the cosmos. On April 15, 2018, NASA extended Cassini's mission for another 2 years, dedicating part of this time to further explore Enceladus and Titan. As Cassini continues to probe these moons, the possibility of finding life looms larger than ever. Enceladus offers a tantalizing glimpse into the potential for life beyond Earth. But it also underscores how fragile life is in the hostile environments of the solar system. On Earth, life thrives thanks to the magnetosphere, an invisible shield protecting the planet from cosmic radiation. However, new evidence suggests this shield is weakening, with dangerous radiation levels emerging above the South Atlantic. It's not a matter of if the Earth's magnetic field will disappear someday, it's a matter of when, one scientist cautioned. The search for life on Enceladus reminds us not only of the possibilities beyond our planet, but also of the delicate balance that sustains life on Earth. As we explore the cosmos, we may learn how to protect our home, and perhaps one day, find another. From the icy mysteries of Enceladus, we now turn our attention to a powerful and invisible force that shapes the cosmos: space weather. This ever-changing phenomenon, driven by the Sun, impacts planets, satellites, and even life on Earth. Let's uncover the secrets of these cosmic storms. Chapter 3. Space Weather. Earth's magnetosphere, a fragile shield. Earth's magnetosphere acts as a vital shield, protecting life from the deadly cosmic radiation that fills the solar system. This magnetic field, emanating from Earth's core, creates a protective bubble around the planet, deflecting the dangerous solar wind. A stream of high-energy, charged particles traveling at up to 1,000,000 miles per hour. Without this defense, these particles would penetrate Earth's atmosphere, causing severe damage to all forms of life. The magnetic field coming out from the Earth makes a big bubble around the Earth, the magnetosphere, that protects us from the most violent actions of the Sun, one scientist explained. If unshielded, these charged particles would pose a dire threat to human health, damaging cells and mutating DNA. If you're in the path of this oncoming charge of particles zipping out from the Sun, and you're not inside some shielding, you're dead. The weakening of the magnetosphere could lead to increased radiation exposure, raising the risk of cancer and other health issues, particularly in regions where the magnetic field is already fragile. Although invisible to the naked eye, scientists have found ways to visualize the Earth's magnetic field. NASA's Dr. Mario Acuna uses a simple demonstration involving a bar magnet and iron filings to illustrate its basic structure. The filings align along the magnetic field lines, forming a pattern that represents the field's geometry, stretching between the magnetic north and south poles. Deep beneath the Earth's surface, approximately 3,000 miles down, lies the source of this field: the planet's molten outer core. The movement of liquid iron and nickel generates a vast magnetic cocoon that extends far into space, enveloping the Earth. This field deflects the solar wind, preventing most of its radiation from reaching the planet. As Professor Dan Lathrop of the University of Maryland explains, the solar wind comes in and hits the bow shock on the magnetosphere and tends to just go around it. The whole thing is shaped kind of like a big tadpole. Most of the radiation ends up streaming past the Earth, but some leaks in at the poles. At the poles, where the magnetic field is weaker, some solar particles penetrate the atmosphere, colliding with gases and producing dazzling auroras, the northern and southern lights. These vibrant displays, while beautiful, are a reminder of the constant battle between Earth's magnetosphere and the Sun's relentless radiation. The stronger the solar wind, the more dramatic the auroras, a researcher noted. But without a magnetic field, this radiation wouldn't be confined to the poles. It would bombard the entire planet, making Earth inhospitable for life. Alarmingly, scientists have discovered that the magnetosphere is already weakening in certain areas. One such region is the South Atlantic anomaly, a vast zone spanning over 3 million square miles off the coast of Brazil. Here, the magnetic field is significantly weaker, allowing cosmic radiation to creep closer to Earth's surface. This anomaly is expanding, raising concerns about its long-term effects. Satellites passing through the region experience heightened radiation levels, often resulting in electronic malfunctions. If the weakening continues, the anomaly could expose more of Earth to dangerous levels of radiation. The magnetosphere is essential to Earth's habitability, yet its stability is not guaranteed. Scientists are racing to understand why this protective field is changing and what the consequences might be for life on Earth. The magnetic field is weakening, one researcher warned. It's not a matter of if the Earth's magnetic field would disappear someday, it's a matter of when. The potential disappearance of this shield raises profound questions about the future of life on Earth and humanity's ability to adapt to a more hostile environment. The fight to preserve and understand Earth's magnetosphere is not just a scientific endeavor. It's a battle for survival against the relentless forces of the cosmos. The South Atlantic anomaly, a mysterious region of weakened magnetic field off the coast of Brazil, offers a sobering glimpse into what Earth might face if its magnetosphere continues to decay. Although scientists don't fully understand the origin of this anomaly, its effects are clear and alarming. NASA scientists have observed its devastating impact on technology. Satellites passing over the anomaly encounter heightened levels of cosmic radiation, leading to frequent malfunctions. The combination of the energetic particles found in the anomaly, along with new particles injected by solar storms, has resulted in total failures of communications spacecraft, one scientist noted. Even the Hubble Space Telescope, a billion-dollar marvel, must shut down sensitive instruments as it traverses the anomaly to avoid irreparable damage. But the consequences may extend beyond technology. As the magnetic field continues to weaken, radiation is creeping closer to the planet's surface. Professor Peter Olson warns that air passengers could be among the first to feel the effects. If you're on a long-haul commercial flight, you might be flying through regions where the magnetic field is weak. At those altitudes, increased radiation could impact the airplane, Olson explained. This could disrupt radio communications, leaving aircraft and passengers vulnerable during flights. The weakening of Earth's magnetic field is not just a modern phenomenon, it has been in decline for centuries. Dr. Mimi Hill uses an unexpected tool to study its history. Ancient pottery. Clay pots contain tiny particles of magnetite, a magnetic iron-based mineral. Normally, these particles are randomly oriented, but when the clay is fired at high temperatures, the particles align with the Earth's magnetic field at that moment. As the clay cools, the magnetic orientation becomes locked in, preserving a snapshot of the magnetic field's strength. By extracting small cores from ancient pots and analyzing them with specialized equipment, Hill calculates the strength of Earth's magnetic field at the time the pottery was fired. Comparing these measurements to modern samples reveals a startling trend. The magnetic field has weakened by 10% since the mid-17th century. Hill's findings support the growing concern among scientists that the magnetosphere is decaying at an alarming rate. Professor Jeremy Bloxham estimates that Earth's magnetic field could vanish far sooner than previously thought. If we could flip a switch and turn off the Earth's magnetic field, it would take about 15,000 years to disappear naturally, Bloxham said. But at the current rate of decay, we could lose it in just 1,500 years. This rapid decline raises urgent questions about the future of life on Earth. Without the magnetosphere, the planet would be exposed to deadly levels of cosmic and solar radiation. Genetic mutations, increased cancer rates, and severe disruptions to ecosystems could become the norm. If Earth's magnetic field were to disappear completely, the consequences would be catastrophic. The solar wind, which is currently deflected by the magnetosphere, would strip away the atmosphere over time, leaving the planet vulnerable to radiation much like Mars today. Understanding why the magnetic field is fading and how to mitigate its effects is now one of the most pressing scientific challenges. The South Atlantic anomaly serves as a warning, and Earth's ancient pottery offers clues, but the ultimate solution remains elusive. As Earth's shield continues to weaken, humanity must grapple with the reality of a more vulnerable planet in an increasingly hostile cosmos. The fate of Mars, a window into Earth's future. Mars, the most Earth-like planet in the solar system, holds critical clues about the importance of a magnetic field in sustaining a planet's habitability. In 1996, NASA's Mars Global Surveyor launched to uncover the secrets of the red planet. Mars shares many similarities with Earth. Both planets have hard crusts, dense cores, and comparable atmospheric chemistry. Billions of years ago, scientists believed that water flowed across Mars's surface, much like on early Earth. But today, the planet is a frozen desert. To understand why Mars underwent such a dramatic transformation, the Mars Global Surveyor collected vital data about its surface and magnetic field. Professor Ben Weiss, using this data, pieced together Mars's magnetic history. Unlike Earth, Weiss explained, Mars today does not have a global magnetic field generated in its core. But if you were to walk around the ancient southern highlands of Mars, you'd encounter fields as strong as Earth's, yet far more chaotic, almost like spaghetti pointing in all directions. The Mars Global Surveyor found certain regions of Mars's crust to be strongly magnetized, indicating that the planet once had a magnetic field. The only way to magnetize rocks is for them to form in the presence of a magnetic field, Weiss noted. This finding confirmed that Mars once possessed a global magnetosphere similar in strength to Earth's today. Weiss's work didn't stop there. While the Mars Global Surveyor couldn't take samples, Weiss analyzed Martian meteorites, rocks blasted off Mars by asteroid or comet impacts that later fell to Earth. These rare samples provided invaluable insights. By placing the meteorites in a highly sensitive squid microscope, a device capable of measuring extremely weak magnetic fields, Weiss uncovered Mars's magnetic history. One particularly ancient sample, over 4.2 billion years old, revealed that Mars's magnetic field was strong during the first 50 million years of the planet's existence. However, Mars's magnetic shield eventually disappeared, and with it, the planet's protection from the solar wind and cosmic radiation. Without this defense, Mars's fragile atmosphere was stripped away, leaving it vulnerable to the sun's relentless energy. When Mars lost its magnetic field, Weiss explained, it lost the shield that was protecting it from the solar wind and cosmic radiation. That had catastrophic consequences for its atmosphere and environment. The solar wind eroded Mars's atmosphere over millions of years, causing its oceans to vaporize and its surface temperature to plummet. The loss of its magnetic field likely spelled the end for any primitive life forms that may have existed. Mars was transformed into the barren red planet we see today, a stark reminder of the crucial role a magnetic field plays in maintaining a planet's habitability. Mars's story raises unsettling questions about Earth's future. As Earth's magnetic field continues to weaken, scientists worry that our planet could face a similar fate. Could the solar wind strip away Earth's atmosphere, leaving it a desolate wasteland? How have Earth and Mars evolved so differently, such that Earth still has a magnetic field while Mars doesn't? Weiss asked. The answer lies in understanding the energy source that powers Earth's magnetic field. Probing Earth's interior. Unlike Mars, Earth still generates a global magnetic field, believed to originate deep within its molten outer core, 3,000 miles beneath the surface. The motion of liquid iron and nickel in this layer produces the geomagnetic dynamo, a process that sustains the magnetosphere. But where does the energy come from to keep this dynamo running? Scientists suspect it may involve radioactive decay or residual heat from Earth's formation. However, to confirm these theories, researchers must explore Earth's interior more thoroughly than ever before. This effort requires cutting-edge technology and creative approaches. From drilling deep into Earth's crust to developing advanced computational models, scientists are racing to understand the processes that sustain our magnetic shield. Mars's fate underscores the delicate balance required for a planet to remain habitable. The disappearance of its magnetic field transformed a potentially life-supporting world into a frozen desert. For Earth, understanding the dynamics of its magnetic field isn't just an academic pursuit, it's a matter of survival. By studying Mars, scientists gain insights into the cosmic forces that shape planets and the precariousness of life in the universe. As Earth's magnetic field continues to weaken, the race to unravel its mysteries becomes all the more urgent. Will we unlock the secrets in time? Or will our planet eventually follow Mars into desolation? The answers lie deep within Earth's fiery core and the lessons Mars has to teach. Understanding the source of Earth's magnetic field is no simple task. Scientists face a significant barrier. The Earth's core, where the magnetic field originates, lies nearly 2,000 miles below the surface, far beyond the reach of any probe or direct observation. We really don't know a lot of detail about what's happening 2,000 miles down because there's no way to send a probe there, a researcher explained. To circumvent this challenge, scientists rely on one of nature's most powerful tools: earthquakes. When an earthquake occurs, let's say in Japan, seismologists place an array of detectors on the other side of the planet and analyze how seismic waves travel through Earth. Seismic waves generated by earthquakes don't travel in straight lines. Instead, they bend, change speed, and alter direction as they pass through layers of different densities and compositions. By carefully measuring these changes, scientists have mapped Earth's internal structure and discovered that it is composed of distinct layers, much like an onion. The crust, Earth's outermost layer, is made of solid rock and is only a few miles thick. Beneath it lies the mantle, a layer of denser, semi-liquid rock. Around 1,800 miles down, is the liquid outer core, a churning sea of molten iron and nickel. At the center is the solid inner core, an iron-rich sphere roughly the size of the Moon and as hot as the surface of the Sun. Scientists believe that this core, particularly the iron and nickel within it, generates Earth's magnetic field. But how? One of the most common misconceptions is that the Earth's core behaves like a giant bar magnet. However, the temperatures deep inside the Earth are far too high for permanent magnetism to exist. Permanent magnets stop working at around 1,200 degrees Fahrenheit, a scientist noted. The core is much hotter than that, so some other process must be responsible for generating Earth's magnetic field. To explore this mystery, Professor Dan Lathrop of the University of Maryland and his team embarked on an ambitious experiment. They constructed a 10-foot mechanical model of Earth's core. Inside this vast sphere is a solid iron ball surrounded by 13 tons of liquid metal. Molten sodium, chosen for its lower melting point compared to iron. The outer sphere rotates, driven by separate motors, mimicking the dynamics of Earth's rotation. The inner core spins even faster, reaching up to 15 revolutions per second. The goal, Lathrop explained, is to understand why some planets generate magnetic fields and others don't. What's the switch that allows a planet to come alive magnetically while others remain dead? As the massive sphere reaches its full speed, something extraordinary occurs. Lines of magnetism begin to arc in and out of the model core, mimicking the magnetic field generated by Earth's core. We can't see the magnetic fields directly, Lathrop noted, but we can measure them with sensors. These sensors allow us to map the magnetic field lines, how they rotate, change, and evolve. The experiment offers valuable insights into how convection currents in the liquid outer core, driven by the planet's rotation and heat from the inner core, generate the dynamo effect that powers Earth's magnetic field. Lathrop's model provides a glimpse into the processes that keep Earth's magnetic field alive. The swirling, churning motion of molten metal in the outer core creates electric currents, which in turn generate magnetic fields. These fields interact and amplify each other, forming the vast protective shield that envelops our planet. As researchers continue to refine their experiments, they edge closer to answering one of Earth's most profound questions. What sustains the magnetic dynamo, and could it ever stop? Lathrop's work brings us one step closer to understanding not just Earth, but the broader dynamics of magnetic fields across the cosmos. The answers may determine not only the future of our planet, but also how we understand the forces that shape worlds throughout the universe. The geodynamo, Earth's magnetic engine. The interaction between Earth's solid inner core and churning outer core creates a phenomenon known as the geodynamo, a powerful, stable, and self-sustaining process that generates the planet's magnetic field. This shield, essential for life, protects Earth from harmful solar and cosmic radiation. Dan Lathrop's experiment, a scaled mechanical model of Earth's core, provides striking insights into the geodynamo. This is showing magnetic field patterns, red coming out, blue going in. It's nothing like I imagined it would be, Lathrop explained, as the lines of magnetism emerged. The geodynamo depends on the flow of molten metal in the outer core, driven by the immense heat radiating from the inner core. However, this system isn't eternal. Over time, Earth's core is slowly cooling, raising the question, could our magnetic field shut down? Mars provides a cautionary tale. Billions of years ago, Mars had a molten core and a strong magnetic shield, much like Earth today. But as a smaller planet, just 40% of Earth's size, Mars cooled more rapidly. Without sufficient heat to sustain its dynamo, the red planet's magnetic field collapsed. Mars's cold core explains why it lost its magnetic shield, Lathrop noted. Without this vital heat, the dynamo shut down, and the planet died. This loss of its magnetic field allowed solar wind to strip away Mars's atmosphere, causing its surface to freeze and its potential for life to vanish. Could Earth face a similar fate? Sure, Lathrop admitted. The Earth's molten core is cooling. Eventually, the inner core will grow larger, and at some point, it could solidify completely. Even before that happens, the magnetic field might shut off. The South Atlantic anomaly, a region of dramatically weakened magnetic field over South America and the Atlantic Ocean, raises concerns that Earth's magnetic shield may already be in jeopardy. However, Lathrop offers a different perspective. The anomaly may not be caused by cooling, but by shifts within the core itself. Earth's magnetic field is not a simple, static force. Unlike a bar magnet, the field is dynamic, constantly shifting and evolving. The magnetic North Pole, for example, is elusive, drifting unpredictably over time. To understand these shifts, Professor Jeremy Bloxham studies centuries-old records of magnetic observations made by sailors during the 17th and 18th centuries. Feeding this historical data into a computer, Bloxham created an animation showing how Earth's magnetic field has changed over the last 300 years. In red and orange, we see where the magnetic field emerges from the core. In blue, we see where it sinks back in, Bloxham explained. Over the past 150 years, the field's overall strength has declined by 10%, a rate far faster than if the geodynamo were simply cooling. More disturbingly, Bloxham's model reveals a reversed polarity patch beneath the South Atlantic anomaly. In this region, the magnetic field points in the opposite direction to what is expected, weakening the shield's ability to deflect cosmic radiation. "This patch is growing," Bloxham warned. "It's a storm brewing under the South Atlantic." The South Atlantic anomaly already stretches over 3 million square miles, encompassing much of South America and the Atlantic Ocean. While cosmic radiation currently affects only satellites and spacecraft passing through the region, its reach is expanding. If the anomaly continues to grow, it could eventually expose Earth's surface to harmful radiation. Where the magnetic field is reversed, cosmic rays that would normally be deflected are reaching the upper atmosphere. Scientists fear that, in time, this radiation could penetrate further, impacting living organisms and critical technology on the ground. The sun will turn from being our friend to our enemy, Bloxham cautioned. The South Atlantic anomaly is a stark reminder of the dynamic nature of Earth's magnetic field and its potential vulnerability. While the anomaly doesn't signal an immediate collapse of the geodynamo, it highlights how Earth's magnetic shield is constantly evolving. Understanding these changes is critical. As researchers like Lathrop and Bloxham continue their work, humanity inches closer to uncovering the mysteries of the geodynamo, the forces beneath our feet, and the delicate balance that sustains life on Earth. The magnetic field has shielded Earth for billions of years, but its future remains uncertain. As we unravel the dynamics of this invisible force, we must prepare for the possibility that the storm brewing beneath the South Atlantic could grow into a planetary crisis. The looming threat of a magnetic reversal. If Earth's magnetosphere were to disappear, the consequences would be dire. High-energy solar radiation would gradually strip away the planet's atmosphere, evaporate its water, and render it uninhabitable. While the magnetosphere continues to protect us, its apparent weakening raises pressing concerns. To prepare for the future, scientists are turning to the past for clues. On July 20, 1969, Neil Armstrong's historic moon landing became a milestone in human achievement. However, during their journey aboard Apollo 11, Armstrong and Buzz Aldrin encountered a bizarre phenomenon. Flashes of light in the darkened spacecraft, visible even with their eyes closed. Upon returning to Earth, they reported their observations, leaving NASA scientists baffled. Years later, researchers concluded that these flashes were caused by high-energy cosmic rays penetrating the spacecraft and interacting with the astronauts' eyes. These cosmic rays, made up of protons, electrons, and other charged particles, originate from the Sun and beyond. For astronauts, cosmic radiation presents a significant danger. Outside Earth's magnetosphere, particularly during a solar storm, the levels of radiation can have devastating health consequences. Prolonged exposure can result in radiation sickness, cellular damage, and long-term health effects. Within Earth's magnetosphere lies a hazardous region known as the Van Allen radiation belts, which trap charged particles in magnetic loops between the poles. These belts present a significant challenge for human space exploration. These are like magnetic bottles where the particles are trapped and bounce back and forth, explained NASA scientist Sten Odenwald. If you were an astronaut in a spacesuit in the Van Allen belts for too long, you would receive a lethal dose of radiation. The effects are not hypothetical. At least 39 astronauts have developed cataracts within 5 years of exposure to radiation during space missions. With a weakening magnetosphere, this risk isn't limited to space travelers. Life on Earth could also face increased exposure. To better understand the state of Earth's magnetic field, Professor Gary Glatzmeyer developed an advanced computer model to simulate its behavior. While the model cannot replicate real-time events exactly, it provides a qualitative look at how the magnetic field evolves over millennia. Running continuously, Glatzmeyer's simulation compresses 100,000 years of magnetic activity into a single year. Around 36,000 simulated years into the experiment, something remarkable occurred. The magnetic poles began to reverse positions. The field was directed inwards here and outwards there, Glatzmeyer explained, describing the dramatic changes at the surface of the model's core. But now, the reversal is occurring. The field is switching. Outwards becomes inwards, and vice versa. This spontaneous swapping of the magnetic north and south poles, known as a geomagnetic magnetic reversals, have occurred multiple times throughout Earth's history, though none have been witnessed by humans. During these periods, a compass needle would point south instead of north. Glatzmeyer's research reveals that reversals are often preceded and followed by a significant weakening of the magnetic field. This phenomenon could provide an explanation for the South Atlantic anomaly, where the magnetic field is currently at its weakest. Scientists are left wondering, is this the early stage of a magnetic reversal? If a magnetic reversal is underway, the implications are profound. During the transition, the magnetosphere would shrink inward, providing less protection against cosmic radiation. This exposure would last for thousands of years, subjecting Earth to dangerous levels of solar and galactic particles. We've never witnessed a reversal, so we don't really know what it would look like, Glatzmeyer admitted. But it would almost surely contract the bubble of the magnetosphere closer to the Earth's surface. The consequences of a magnetic reversal could be catastrophic for species that depend on this field for survival. Earth's magnetic field has reversed thousands of times in its 4.2 billion-year history, with significant drops in strength preceding each event. Many scientists now believe the next reversal is imminent. To better understand and predict this phenomenon, the European Space Agency, ESA, launched the SWARM mission in 2013. This fleet of satellites is designed to generate detailed, real-time maps of Earth's magnetosphere and monitor its changes. SWARM's data provides critical insights into the processes driving the field's weakening, helping scientists anticipate its future behavior. As the magnetic field continues to weaken, life on Earth faces unprecedented challenges. From increased exposure to harmful radiation to the disruption of animal navigation, the consequences of a reversal will ripple across ecosystems and human civilization. Understanding the timing and implications of a magnetic reversal is no longer just a scientific curiosity. It's a necessity. The race to prepare for this event underscores humanity's reliance on the invisible shield that has protected life for billions of years. While the exact timing of the next reversal remains uncertain, the evidence is clear. Earth's magnetic field is changing, and the time to act is now. Whether through technological advancements or deeper scientific inquiry, the answers we seek may ultimately safeguard the future of life on Earth. Preparing for a magnetic reversal, the SWARM mission, and humanity's adaptation. Professor Niels Olsen of the Danish National Space Center is at the forefront of efforts to understand and predict the behavior of Earth's magnetic field. He is part of the European Space Agency's SWARM mission, an innovative project involving 3 satellites that are set to revolutionize our understanding of the geodynamo and its effects. The new and exciting idea behind SWARM is that we have 3 satellites, Olsen explains. We have a higher satellite at an altitude of 530 kilometers and a pair of satellites at about 430 kilometers. Equipped with advanced new-generation magnetometers, these satellites are designed to detect even the tiniest variations in magnetic field strength and to pinpoint any emerging areas where the poles might be reversing. The SWARM mission offers an unprecedented glimpse into the movement of molten iron in Earth's core, the driving force behind the magnetic field. I think it's amazing that we can take magnetic measurements from satellites flying a few hundred kilometers above Earth and infer how the molten iron moves at a depth of about 3,000 kilometers. Isn't that incredible? Olsen marvels. By closely monitoring these subtle changes, scientists hope to predict the timing of a magnetic reversal and develop strategies to mitigate its impact. While humanity cannot directly influence the geodynamo, advancements in forecasting technology could save lives. In the next decade or two, we might develop the ability to forecast where the magnetic field is headed, Olsen notes. This could be used as a planning tool for satellite operations, manned space flights, and even ground-based technologies to prepare for an impending reversal. As the magnetosphere weakens, cosmic radiation will penetrate closer to Earth's surface, potentially disrupting communication systems, power grids, and aviation. However, life on Earth has historically adapted to these changes. Although the drop in magnetic field intensity would affect life adversely in some ways, life on Earth has found ways to survive these events in the past, Olsen reassures. The weakening of Earth's magnetic field will be visible in the skies as auroras, typically confined to polar regions, begin to appear across the globe, even in equatorial areas. These dazzling displays will serve as a reminder of the magnetosphere's decline and its critical role in protecting life. The magnetosphere has been a cornerstone of Earth's evolution, shielding the planet from deadly solar storms and cosmic radiation. Without it, Earth would be barren, unable to sustain life as we know it. Though all life will be affected by a magnetic reversal, scientists have yet to find evidence linking past reversals to mass extinction events. This suggests that with adaptation, humanity can survive the challenges posed by a shifting magnetic field. If we adapt, we should survive, Olson concludes. Beyond the magnetosphere's reversal lies another looming danger: solar storms. The Sun, a life-giver, also harbors the potential to unleash a weapon 100 million times more powerful than an atomic bomb. A direct hit from a massive solar flare could black out entire continents, plunging human civilization from the space age to the Stone Age in an instant. It's not a question of if, but when the next major event will happen, a scientist warns. We've been hit before, and we're in the Sun's sights again. As the Swarm mission continues its vital work, humanity must recognize the interconnected threats posed by a weakening magnetic field and solar activity. By advancing scientific research and technological preparedness, we can navigate these challenges and safeguard our planet for future generations. As we delve deeper into the mysteries of space weather, one force looms above all others: the Sun. Beyond its warmth and light lies an untamed power capable of reshaping life on Earth in an instant. Welcome to the final chapter, Solar Storms, where the Sun's might becomes both awe-inspiring and terrifying. Chapter 4: Solar Storms. The anatomy of a solar storm. Unraveling the Sun's hidden power. March 13, 1989, will forever be remembered in Quebec's history as the night the city plunged into darkness. At precisely 2:44 a.m., a 100-ton transformer on Montreal's power grid violently overloaded, triggering a massive blackout that left 6 million people powerless. The chaos was swift and unforgiving. Within 90 seconds, the entire grid collapsed, casting Quebec into an eerie darkness. Temperatures dropped to 8 degrees Fahrenheit, and life or death operations in hospitals were sustained only by emergency generators. Although the power was restored after 12 hours, experts agree the disaster could have been far worse. With just a few more damaged components, the entire east coast of the US could have gone down too, warned astronomers. What caused this sudden and devastating blackout? It wasn't human error or a terrorist attack. It was a phenomenon far beyond Earth's atmosphere. The culprit was a solar storm, triggered by an immense explosion on the Sun's surface 93 million miles away. 3 days before the blackout, astronomers at the Space Weather Prediction Center in Colorado observed a highly active region on the Sun. Suddenly, a gigantic explosion, a solar flare, erupted, sending a wave of radiation hurtling through space at millions of miles per hour. As the wave reached Earth, it ignited stunning auroras across the skies, visible from Alaska to Mexico. But along with this spectacular display came a surge of energy so immense it disrupted Earth's magnetic field, overloading transformers in Quebec and plunging the region into chaos. Solar storms like the one in 1989 are awe-inspiring in their scale. Space weather scientist Joe Conches describes the sheer magnitude of these events. Billions or trillions of tons of matter are thrown off the Sun at about 1,000,000 miles per hour. It boggles the mind to compare this to terrestrial weather. Even the strongest hurricanes or tornadoes with wind speeds of hundreds of miles per hour pale in comparison. The 1989 solar storm remains one of the most destructive in recorded history, but it is not an isolated event. The Sun is capable of far more powerful storms, with the potential to cripple entire continents. In today's technologically advanced world, the consequences of a major solar storm could be catastrophic. Our reliance on the electric power grid and interconnected technologies makes us more vulnerable than ever before. A solar storm of sufficient magnitude could disrupt power grids, satellites, communication systems, and even transportation, warns a leading scientist. In the 21st century, losing power over a continent, even temporarily, would be a major disruption to society. Understanding solar storms is now more critical than ever. Scientists are racing to unravel the mysteries of these cosmic events. What triggers them? How they interact with Earth's magnetic field? And what can be done to mitigate their effects? By studying the anatomy of solar storms, we may one day develop technologies to protect our power grids and infrastructure. But for now, the Sun's immense power remains a reminder of the delicate balance between the freedom our technology brings and its potential vulnerabilities. The next storm may be on the horizon, and this time, we might not be so lucky. Unleashing the Sun's fury. Solar flares and their terrifying power. The investigation into solar storms begins deep within the Sun, a 900,000-mile-wide ball of gas so massive it could hold over 1,000,000 Earths with room to spare. At its heart lies a nuclear powerhouse, where temperatures soar to an unimaginable 27 million degrees Fahrenheit. Here, hydrogen atoms fuse to form helium, releasing an astounding 5 million tons of energy every second. This process generates more energy in a second than humanity has used throughout its existence. Yet, the Sun's energy is not its only byproduct. The same nuclear activity produces enormous magnetic fields, which loop across the surface, bubbling up from the core and extending hundreds of thousands of miles into the solar atmosphere. The Sun's rotation adds to the complexity of its magnetic field. Unlike Earth, where the entire planet rotates uniformly, the Sun's equator rotates faster, taking 25 days to complete a revolution compared to 35 days at its poles. This difference stretches and distorts the magnetic loops, twisting them into unstable, spiraling structures. These magnetic loops carry billions of tons of superheated plasma, a searing mixture of electrically charged protons and electrons. A single loop contains as much energy as 10 million volcanic eruptions occurring simultaneously. When these loops collide, they unleash a phenomenon that astronomers call a solar flare. An explosion so powerful, it dwarfs anything experienced on Earth. To understand how these magnetic loops cause solar flares, Professor Paul Bellin has created a model of the Sun's surface in his laboratory. Using magnetic fields and electrically conductive plasma, he mimics the conditions found on the Sun. We set up a magnetic field that is arched, with plasma flowing along it, and then drive an electric current through the system, just like on the Sun, Bellin explains. His experiments reveal the unstable nature of these magnetic loops. They twist, stretch, and collide with each other. When they short-circuit, all their energy is released in an intense spark, a scaled-down version of a solar flare. It's like seeing a hurricane develop, Bellin says. The magnetic fields and electric currents interact, and when the forces add up just right, the entire structure explodes. The energy released by Bellin's lab experiments is minuscule compared to real solar flares. A large solar flare unleashes energy far greater than anything on Earth, with no terrestrial counterpart. The smallest flares release energy equivalent to 1 million nuclear bombs. The largest are a staggering 1,000,000 times that. A single large solar flare could power the United States for thousands of years. But the destructive potential is equally massive. If such energy were unleashed on Earth, the explosion would level cities, sending shockwaves across the globe and wiping out nearly all life. In 1997, NASA captured an image of the Sun's surface immediately following a solar flare. The photograph revealed a shock wave, a ripple of energy racing thousands of miles across the solar surface at a speed so fast it could circle Earth in under a minute. Dr. Carol Shriver, who studies solar flares, underscores their overwhelming power. A large flare is a vast amount of energy. It has no counterpart on Earth. These flares are a stark reminder of the Sun's dual nature. While it sustains life on Earth, its eruptions possess the power to devastate the planet. Understanding these phenomena is vital to mitigating their impact. As we become increasingly reliant on technology, the stakes grow higher. A direct hit from a massive solar flare could knock out satellites, disrupt communication systems, and cripple power grids worldwide. Preparing for this threat requires unraveling the mysteries of solar storms and finding ways to shield Earth from their fury. The Sun's awesome power is a humbling reminder of the fragile balance that sustains life on Earth, and the constant vigilance needed to protect it. The hidden dangers of solar storms, a cosmic threat. While solar flares capture the imagination with their fiery explosions, they are only the opening act of a much larger event. Like the flash of a gun, the true damage comes from what follows. The coronal mass ejection, CME. These immense clouds of charged particles, driven by the Sun's magnetic activity, race through space at millions of miles per hour, carrying the power to disrupt life on Earth and beyond. Solar flares and CMEs create havoc not just on Earth, but also in the realm of outer space. One of the most famous casualties of solar storms was Skylab, America's first space station. Launched on May 14, 1973, Skylab aimed to expand humanity's understanding of space and test the limits of long-term human habitation in orbit. Despite its ambitious mission, Skylab faced numerous mechanical challenges. By 1974, it was abandoned by its crew and left in orbit, awaiting repairs that would never come. Over the next 5 years, the Sun unleashed a series of powerful solar flares, accompanied by waves of intense radiation. These waves, traveling at the speed of light, smashed into Earth's upper atmosphere, heating it dramatically. Temperatures in the upper atmosphere rose by as much as 1,500 degrees Fahrenheit, causing it to expand outward by up to 1,000 miles. This swelling enveloped Skylab, creating atmospheric drag where there had previously been none. Slowed by this drag, Skylab's orbit decayed rapidly. By July 1979, Skylab plummeted to Earth, burning up during re-entry. The fate of Skylab serves as a cautionary tale for modern space technology. Without regular boosts to maintain altitude, thousands of satellites could face a similar demise. Even the International Space Station, ISS, a marvel of human engineering, is not immune. The ISS typically loses about 75 yards of altitude daily, but during solar storms, it can lose significantly more. This risk extends beyond infrastructure. NASA scientist Niels Zapp emphasizes the critical danger solar storms pose to astronauts. Our major problem is that we don't have control over the situation. We can't simply evacuate astronauts from orbit or shield them adequately once a solar storm begins. Radiation from solar storms can penetrate spacecraft and spacesuits, causing severe damage to human cells and DNA. For astronauts on missions beyond Earth's magnetosphere, such as future journeys to Mars, the stakes are even higher. Solar storms have already brought humanity dangerously close to disaster. In 1972, during the gap between the Apollo 16 and Apollo 17 missions, the Sun unleashed a massive storm. Had astronauts been on the Moon's surface during this event, they would have been exposed to 10 billion tons of radiation, enough to cause fatal harm. The timing of the storm was a narrow miss for the Apollo program and a stark reminder of the risks posed by the Sun's unpredictable behavior. Today, scientists are working tirelessly to predict when and where the next solar storm will strike. But the speed and power of these cosmic events make early warning nearly impossible. A CME can travel from the Sun to Earth in as little as 18 hours, leaving little time for preparation. As our world becomes more dependent on technology, from satellites to power grids, the need to understand and mitigate solar storms grows ever more urgent. Solar storms are not just astronomical phenomena. They are existential threats that could reshape our way of life in an instant. Whether safeguarding satellites, protecting astronauts, or preserving the integrity of our power systems, humanity must rise to meet the Sun's challenge, or risk being caught off guard. The fury of a coronal mass. Ejection, unlike solar flares, which are bursts of energy and light, coronal mass ejections, CMEs, are cataclysmic explosions of matter from the Sun's corona, its outermost layer. These eruptions launch billions of tons of charged particles into space, traveling at speeds up to 1,000,000 miles per hour. When aimed at Earth, a CME carries the potential to wreak unprecedented havoc on our technology and infrastructure. The corona, extending millions of miles from the Sun's surface, is a seething cauldron of superheated plasma. Temperatures here soar to nearly 3 million degrees Fahrenheit, making it almost 200 times hotter than the Sun's visible surface. This disparity has puzzled scientists for decades. How can the outer atmosphere be exponentially hotter than the surface below? The answer lies in the Sun's magnetic fields. These magnetic lines of force twist and tangle as the Sun rotates, creating immense pressure and energy. Occasionally, the magnetic field lines snap and reconnect, releasing vast amounts of energy in the form of a CME. A CME begins with the sudden destabilization of the magnetic field in the corona. This destabilization can occur when magnetic loops, already under strain, collide and release their pent-up energy. The result is a violent ejection of plasma, a mixture of protons, electrons, and other particles into the solar system. As the CME expands, it forms a giant bubble of solar material that grows larger as it moves away from the Sun. If Earth lies in its path, the collision with our magnetosphere can have devastating consequences. On March 13, 1989, Quebec experienced the catastrophic impact of a CME. While the aurora borealis illuminated the skies with mesmerizing colors, the second wave of radiation from the Sun's eruption arrived. As the CME struck Earth's magnetosphere, the charged particles caused powerful geomagnetic currents to flow through the planet's magnetic field. These currents induced surges of electricity in the power grid, overloading transformers and causing the entire province to lose power. The blackout plunged 6 million people into darkness, halting life in its tracks. Hospitals relied on emergency generators, businesses came to a standstill, and temperatures dipped dangerously low, threatening lives. Quebec's power outage was a stark warning. Our modern reliance on interconnected power grids and electronic systems makes us increasingly vulnerable to solar storms. The effects of a CME extend far beyond blackouts. High-energy particles can disrupt communication satellites, GPS systems, and even aircraft electronics. During severe solar storms, flights near the poles are diverted to lower altitudes to avoid losing contact with air traffic control. Satellites are particularly at risk, as the intense radiation can damage sensitive electronic components, rendering them useless. The Hubble Space Telescope and other vital systems are often shut down during solar storms to prevent irreparable damage. Understanding and predicting CMEs is now a critical focus for space weather scientists. NASA's Solar and Heliospheric Observatory, SOHO, and other satellites monitor the Sun around the clock, searching for early signs of these colossal eruptions. However, even with advanced technology, CMEs travel so quickly, sometimes reaching Earth in 18 hours, that early warning systems are limited. Preparing for their impact remains a challenge, as the energy unleashed by a CME can ripple through global infrastructure in seconds. Quebec's blackout was caused by a moderate CME. Larger eruptions, like the Carrington event of 1859, could have far more devastating consequences today. In our digitally connected world, a Carrington-scale event could cripple power grids, disrupt communication networks, and cause trillions of dollars in damage. As the Sun continues its cycle of activity, scientists race to unlock the secrets of CMEs and develop strategies to protect Earth from their worst effects. For now, the Sun's immense power serves as both a reminder of our planet's vulnerability and a call to action for humanity to safeguard its future. Unlocking the history of solar storms in ice deep within the Arctic Circle, layers of ancient ice hold a pristine record of Earth's encounters with the Sun's most violent outbursts. These frozen archives have preserved evidence of solar storms stretching back thousands of years, offering scientists a glimpse into the past to better prepare for the future. One of the key indicators of a past solar storm is nitrate, a chemical produced when high-energy particles from the Sun interact with Earth's upper atmosphere. These particles generate a cascade of reactions, resulting in elevated nitrate levels that eventually settle onto the surface and become trapped within layers of accumulating ice. By extracting ice cores, researchers can analyze these chemical signatures to reconstruct the timeline and intensity of historic solar storms. Each layer of ice corresponds to a specific year or season, much like the rings of a tree. By carefully measuring the nitrate concentrations in these layers, scientists identify spikes that coincide with major solar events. We've found that spikes in nitrate levels match perfectly with documented storms in recent history, explains one researcher. This validates the method and allows scientists to extend their analysis further back in time, revealing storms that occurred long before humans began recording them. The ice core data reveals a chilling pattern. While moderate solar storms are relatively common, catastrophic events, on the scale of the Carrington event of 1859, occur far less frequently. Yet, their impact is far-reaching. The Carrington event remains the most powerful solar storm ever documented. It produced auroras so bright they were visible as far south as the Caribbean and lit up the night sky with hues of red and green. Telegraph systems worldwide failed, and in some cases, operators reported receiving electric shocks from their equipment. Ice core records show that similar events have struck Earth several times in the past few thousand years. These events serve as stark reminders of the Sun's immense power and the vulnerability of modern civilization. In today's world, the stakes are much higher. The interconnected nature of global infrastructure, power grids, communication networks, satellites, makes society far more susceptible to the effects of a solar superstorm. A Carrington-scale event today could result in widespread power outages, GPS failures, and disruptions to essential services, such as healthcare and banking. Entire regions could be plunged into darkness, and recovery could take weeks, months, or even years. With each passing year, the Sun edges closer to its next solar maximum, the peak of its 11-year activity cycle. This increases the likelihood of powerful solar flares and CMEs. To mitigate the risk, scientists are working to improve early warning systems, monitor solar activity more closely, and strengthen the resilience of power grids and satellite systems. The ice core records provide a critical baseline for understanding the frequency and intensity of solar storms, reminding us of the need to stay vigilant. As one scientist notes, the storms of the past are not relics, they're previews of what's to come. The next solar superstorm may be decades away or just around the corner. Either way, the Earth's frozen history offers invaluable lessons for protecting our future. Exploring the cataclysmic power of superflares. The Orion Nebula, a stellar nursery 1,500 light-years away, holds an astonishing secret. As Hubble's X-ray images reveal, nearly every star in this region is capable of unleashing colossal bursts of energy known as superflares. These events dwarf anything experienced on Earth, producing eruptions thousands or even tens of thousands of times more powerful than the strongest solar flares from our Sun. Over a span of just 13 days, X-ray observations show a dazzling spectacle of repeated bursts, each flash representing a release of energy far beyond Earth's capacity to endure. Such superflares, if aimed at a nearby planet, wouldn't merely disrupt technology or cause blackouts. They could obliterate the atmosphere, sterilize the surface, and potentially destroy all life. Astrophysicist Eric Felsen reflects on the implications. What we're seeing in regions like the Orion Nebula is a level of energy release that's entirely foreign to us. These young stars, in their hyperactive early stages, behave like cosmic flamethrowers, regularly unleashing superflares capable of reshaping entire solar systems. Superflares are born from the same principles as smaller solar flares: magnetic instability. On stars, tangled magnetic fields stretch, twist, and collide, releasing catastrophic amounts of energy. The intense activity in young stars stems from their rapid rotation and turbulent interiors, which amplify these magnetic processes. The energy released in a single superflare could power Earth's global energy needs for billions of years. Yet in stellar terms, these eruptions are not uncommon. Stars in their youth, like those in the Orion Nebula, flare frequently as they stabilize and mature. This chaotic behavior is an integral part of their evolution. For humanity, the idea of a superflare striking Earth may seem like science fiction. Thankfully, our Sun, a relatively stable and middle-aged star, is unlikely to produce such an event. However, as we look toward the stars for potential colonization, the threat of superflares becomes a significant consideration. Imagine a colony established on a planet, orbiting a young star like those in the Orion Nebula. The planet's inhabitants might enjoy a world bathed in vibrant light and warmth, but they would also face a grave danger. One massive superflare could strip away the planet's protective atmosphere, exposing its surface to lethal radiation and rendering it uninhabitable. Dr. Felsen explains, superflares on these stars are regular and inevitable. Any attempt to settle in their vicinity would require extraordinary measures to shield life from their devastating effects. Understanding these phenomena is essential for future interstellar exploration. While superflares pose a danger, they also provide scientists with a unique opportunity to study magnetic processes on a scale impossible to replicate on Earth. Observing these cosmic events helps researchers understand the life cycle of stars, the formation of planets, and the conditions that make life possible or impossible. The sheer power of superflares serves as a humbling reminder of the volatile nature of our universe. The Sun's relative stability has been a crucial factor in the development and persistence of life on Earth. But beyond our solar system, chaos reigns. Regions like the Orion Nebula remind us that the cosmos is as violent as it is beautiful. As scientists continue to peer deeper into the universe, they uncover both the risks and the resilience of life. Superflares might appear as a destructive force, but they also drive the evolution of stars and the shaping of worlds, ultimately contributing to the dynamic balance that governs the cosmos. The early Sun, a forge of solar storms and planetary birth. Young stars, like those in the Orion Nebula, offer a glimpse into the tumultuous past of our Sun. These stellar infants, barely 1 million years old, are chaotic powerhouses of magnetic activity, spinning rapidly and unleashing colossal flares. Gibor Basri, a space scientist, explains the connection. The faster a star spins, the greater its magnetic activity. This is why the young Sun, spinning once every few days compared to its current once-a-month rotation, was far more active and violent. Eric Felsen paints a vivid picture of the early Sun. When the Sun was a baby, it was 3 times its current size, glowing a ruddy orange with gigantic star spots. Magnetic fields, invisible to the human eye but immense in X-ray vision, extended 10 times the star's diameter, crackling with energy. This turbulent star shaped the very solar system we inhabit today. Around 4.6 billion years ago, the solar system was a chaotic disk of gas and dust orbiting the nascent Sun. Scientists believe that the violent early Sun played a crucial role in shaping this material into planets. Massive solar storms, driven by magnetic turbulence, ripped through the dust disk, forcing tiny particles to collide and stick together. Initially, the dust particles were as fine as cigarette smoke. Felsen describes the challenge. It's a mystery how you go from microscopic dust grains to asteroids. Sticking together snowballs is easy, but sand grains? That's much harder. However, the young sun's explosive energy helped overcome these hurdles. Over time, dust grains fused into larger clumps, eventually forming the first embryonic planets. As the sun aged, its rotation slowed, and its magnetic activity calmed. This gradual stabilization allowed the planets to form more peacefully and set the stage for life to develop in the solar system. Had the sun remained in its violent infancy, Earth might never have supported life. Though the sun is now a middle-aged star, its occasional tantrums still have a profound impact on Earth. Solar storms, fueled by the same magnetic forces that shaped the early solar system, remain a serious threat to modern technology. A massive solar storm could cripple power grids, disrupt communication systems, and cause widespread chaos. The only way to protect our infrastructure is to predict these storms and shut down vulnerable systems before they strike. But forecasting solar storms is a formidable challenge. In September 2006, Japan launched the Hinode satellite, a pioneering mission aimed at decoding the sun's magnetic behavior. Hinode orbits 370 miles above Earth, its advanced instruments capturing the most detailed images of the sun ever recorded. Its mission: to understand the sun's magnetic fields and predict solar storms. In December 2006, Hinode made a groundbreaking observation. The satellite captured footage of a magnetic arc snapping, a precursor to a massive solar flare that erupted at over 1 million miles an hour. This event marked a significant milestone in solar research. Carol Schreiber, using data from Hinode, generated the first computer model of a solar storm before it erupted. This detailed map revealed the complex interplay of magnetic forces that drive solar activity. Understanding these patterns is key to predicting future storms. Solar storms are an ever-present danger in the 21st century, with our reliance on electricity and technology making us more vulnerable than ever. The insights gained from Hinode are invaluable, but scientists are in a race against time to perfect storm forecasting. We need to know when and where the next solar storm will strike, Schreiber emphasizes. The stakes are higher than ever. As researchers continue to study the sun's magnetic fields, the hope is that future predictions will allow humanity to brace for the sun's inevitable tantrums. By understanding our star's behavior, we not only protect ourselves, but also gain deeper insights into the forces that shaped our solar system billions of years ago. Decoding solar flares. The key to prediction. Solar flares, driven by the sun's magnetic fields and electrical currents, are among the most powerful events in our solar system. These electrical currents originate deep within the sun's interior, rise to the surface, and become visible as magnetic arcs. Dr. Carol Schreiber explains, each of these strands represents an electrical current, preformed in the sun's interior and ready to power a flare as it bursts through the surface. Schreiber's three-dimensional models offer unprecedented insights into these phenomena. By tilting the model, the intricate pathways of electrical currents become clear. Rivers of red energy looping 15,000 to 20,000 kilometers above the solar surface before plunging back down. These magnetic rivers hold energy equivalent to 1 billion atomic bombs. When a flare erupts, it releases this energy in a matter of seconds, Schreiber adds. The scale is staggering, 1 million times 1 million atomic bombs going off simultaneously. If scientists can identify these tightly packed magnetic fields before a flare erupts, they might be able to forecast solar storms with greater precision. While advanced technology like HiNode works toward improving predictions, current methods still rely on techniques developed nearly 400 years ago. Analyzing sunspots. Sunspots form when magnetic arcs block the sun's atmosphere from heating certain areas of its surface. As a result, these cooler regions, at about 6,300 degrees Fahrenheit compared to the surrounding 10,000 degrees Fahrenheit, appear as dark spots. Sunspots are not static. They come and go in an 11-year cycle of solar maximums and minimums. During solar minimum, sunspot activity is low, and solar flares are rare. Conversely, at solar maximum, up to 200 sunspots may appear, unleashing intense magnetic activity and frequent solar flares. A week before the Quebec blackout in March 1989, astronomers identified a cluster of sunspots on the sun's eastern limb. This group heralded a period of heightened activity, as the blackout occurred during a solar maximum. The sunspot cycle provides a critical clue. It indicates when the sun is more likely to produce solar storms. However, it doesn't pinpoint the timing or direction of a specific event. Magnetic arcs, the precursors of flares, can cross unpredictably, pulling the trigger on an eruption that reaches Earth in just 8 minutes, far too quickly for any warning. Unlike solar flares, coronal mass ejections, CMEs, are slower, taking up to 4 days to travel from the Sun to Earth. These massive ejections of plasma and magnetic fields hold 10 billion tons of matter spread over millions of square miles. Despite their slower pace, CMEs are the most destructive aspect of solar storms, capable of overwhelming Earth's magnetosphere and inducing powerful electrical surges on the ground. At the Space Weather Prediction Center, scientists constantly monitor solar activity. They scrutinize data for signs of increasing sunspot activity or potential CMEs. One researcher explains, "We're looking at what the sun is doing in real time and trying to predict how those changes will impact Earth." However, the science of space weather forecasting is still in its infancy. Satellites have only observed the solar maximum 3 times. Space weather forecasting today is where Earth weather forecasting was 50 years ago. An expert observes, "We can't yet measure the key factors needed to predict a solar storm with precision." Unlike hurricanes, which are visible and trackable, solar storms are invisible once they leave the sun's surface. Despite their immense size, they spread out over millions of miles, making detection and prediction extremely challenging. Advances in technology and understanding hold promise, but the threat of solar storms remains ever present. Each step toward improving predictions is critical to protecting Earth's power grids, satellites, and infrastructure. As scientists push the boundaries of space weather forecasting, the race is on to better understand the sun's complex behavior and prepare for the next solar storm. A look ahead. Preparing for the next solar storm. The prospect of solar storms has shifted from scientific curiosity to urgent reality. With satellites like Stereo now providing critical 3-dimensional views of the sun and its behavior, humanity has taken significant strides toward predicting the impact of these colossal cosmic events. Yet, the challenge remains daunting. The arrival of a solar storm is imperceptible to the naked eye. With just a handful of atoms per cubic foot, they are more diffuse than the vacuums created in high-tech laboratories. Even sophisticated satellite instruments face difficulties estimating the precise speed of an approaching storm. It's like a batter at a baseball game, explains one scientist. As the ball hurtles toward the hitter, judging its exact speed can be almost impossible. A wrong judgment could cost us dearly. With coronal mass ejections capable of delivering devastating blows to our modern infrastructure, stereo represents a lifeline. Launched in 2006, the two-stage satellite system provided an unprecedented view of the Sun. By orbiting the Sun at slightly different trajectories, the satellites generate stereo images that reveal the intricate dynamics of solar activity. This leap in technology is pivotal. Previously, Earth had only hours to prepare for a CME impact. Now, stereo allows scientists to stretch early warning times to days, potentially averting blackouts like the one that plunged Quebec into darkness. However, stereo is just the beginning. The dream of predicting solar storms before they erupt is closer than ever. With advancements in computational power and increasingly sophisticated solar models, researchers are nearing the point where they can forecast solar behavior with unprecedented accuracy. It won't be next year, but the ability to predict these events well in advance is within our grasp, says a scientist. We're refining our models with higher resolutions and fewer assumptions. Soon, we'll have the tools to anticipate solar flares and CMEs before they're born. The stakes couldn't be higher. For over 2 million years, solar storms posed no threat to life on Earth. But in the last 2 centuries, as humanity harnessed electricity, our dependence on technology has made us vulnerable to the Sun's tantrums. The next solar maximum looms just 3 years away. Once again, Earth finds itself in the firing line. How well we weather the next storm depends on our readiness and the advancements made in solar forecasting. As we conclude this exploration of the Sun's power and its impact on our fragile blue planet, one thing is clear. The Sun is both our life-giver and a potential threat. Its storms remind us of our place in the vast cosmos and the delicate balance that sustains life. Stay curious, stay prepared, and keep looking to the skies. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.